All right, lesson 8. Why isn't the ocean super acidic? So in lesson 8, we took a look at 3 graphs, and each of those graphs gave us some information between ocean pH levels and our carbon dioxide concentrations. So starting off with graph number 3. So in graph number 3, we see right over here, the more carbon dioxide we dissolve, our pH levels are decreasing. So our pH levels are dropping. So we talked about this already before. Why is that happening? So we know that the carbon dioxide in the atmosphere is going into our water, going into our ocean water, and that's colliding with water molecules. And once it collides with water molecules, it is forming that carbonic acid that we've talked about before. So there's our carbonic acid. So now that we're forming this carbonic acid, that's going to have a chance to start colliding with water molecules, right? So we're still in the ocean. So carbonic acid now, wow, what a lovely H, is going to collide with these water molecules. And because of this collision here, water has a higher kinetic energy than the carbonic acid's bonding energy. It's going to knock off that hydrogen ion and add it to itself. So we're going to end up with H3O plus. And if we remember what H3O plus is, it starts with the letter H, is hydronium, right? So hydronium ions are formed from this reaction. So we get this increase of hydronium ions. So because of this increase of hydronium ions, we have a decrease in pH, and that's why our pH level is dropping. So here we see it in graph form, and we also see it in graph number 2, right? So we have our pH, shown in blue, is decreasing. So we have a decrease of pH levels. That's one thing we see in this carbon dioxide time series graph. And we also see the atmospheric carbon dioxide over time is increasing. And we also get one more piece of information, is the dissolved carbon dioxide in water is also increasing. So we have 2 things happening here. We have the atmospheric carbon dioxide increasing and the dissolved carbon dioxide increasing as well, and having a drop of pH. So all this stuff is happening, right? So we took a look at, in lesson 8b, our Sodacan investigation, or POP, right? So POP Sodacan, whatever you prefer. So in this one, we took a look at this data here. So a pop can was opened, a gas was observed leaving. And as this gas was leaving, there was measurements taken at the 0-minute mark, 1-minute mark, 2-minute mark, and so forth. So looking from here to here, we can see that the mass of our can is decreasing, right? So our mass is decreasing, but wait, after a while, it is stabilizing. So it's remaining constant after a while. So that just means staying the same, right? So our mass after a while just stays the same. And what we're going to talk about is we're going to just try to break this down and see like why that's happening. So one concept that you may or may not have heard of in chemistry is diffusion. So what is diffusion? So diffusion is the spreading of a gas from a high concentration to low concentrations. So we all exert gas at different times, right? Like one thing that could happen is we may fart, right? So we may fart, and as we fart, the concentration of gas or poop particles are really, really high by us. And that's going to diffuse out into the air where there's lower concentrations. And so that's why we may not smell it if someone's farting nearby us until a little bit, because those poop particles have to travel to our nose. And so that's how gases act. They go from a high concentration to a low concentration spot. So taking a look at our soda can, or our pop can, we've opened it up, and we've taken those time interval or those measurements at those time intervals, and we saw that the mass started to decrease. So we saw a slight decrease in our mass over time, and that's because our carbon dioxide is leaving. So we had carbon dioxide diffuse out into the air. So our carbon dioxide was just going out there. So we were losing CO2, right? And that's why our mass was decreasing. But at some point, our mass started to stay the same. So let's take a look at that next point. So there is another term here. And this term, most likely you have not heard this before. Maybe you have, maybe you haven't. But if you haven't, there it is, equilibrium. So equilibrium. Equilibrium, you could think of this key term in equilibrium, equal, right? So the rate of the forward reaction equals the rate of the reverse reaction. So this is a little bit of a tricky concept. So we already know that our carbon dioxide is leaving. Let me switch colors over here. We'll go with red. So we already know that our carbon dioxide is leaving, right? So initially we're losing a bunch of carbon dioxide gas. That's why our mass is decreasing. One thing that we've learned in earlier lessons is carbon dioxide goes into the ocean as well, right? So that's the same thing with our pop and soda water. Not soda water, excuse me, our pop and soda liquid, right? So this stuff is also going back into there. So we're losing some carbon dioxide, but we're also gaining some carbon dioxide into our liquid. So our rate is, so our reverse rate and our forward rate. So all that means is eventually our mass stabilizes, because even though carbon dioxide is escaping, also carbon dioxide is going into our liquid as well. So when the rates of those are equal, so when we have an equal amount of carbon dioxide, equal rate of carbon dioxide leaving our soda, as well as an equal to the rate of carbon dioxide going into the soda, that's when we've reached this thing called equilibrium, and those concentration is going to look the same. So our mass is going to stay constant at that point. So kind of relating it back to why isn't the ocean super acidic? So we know there's more carbon dioxide in our atmosphere, right? So we know there's more carbon dioxide in the atmosphere, and that carbon dioxide is diffusing into our ocean water. So one thing that's happening is we have this stuff diffusing into the ocean. And as the carbon dioxide is diffusing, so our ocean is becoming more acidic because of the creation of carbonic acid and then the creation of hydronium ions. But because of that, carbon dioxide molecules are also always moving. So our carbon dioxide particles are always moving as well. So those are just constantly moving. And so as likely as it is for it to come out, CO2 is also leaving our ocean water. So our CO2 is also leaving the ocean. So it's going back into the atmosphere. So it reaches that equilibrium when the rate of the carbon dioxide going from the air into the water is equal to the rate of the carbon dioxide leaving from the water into the air. And even though this is the reason why our ocean isn't super acidic, the ocean is still acidic because we are sending more carbon dioxide out into the atmosphere because of because we started burning fossil fuels, and so there's a lot more carbon dioxide into the atmosphere, and that's why we saw in graph number 2, we're increasing our atmospheric carbon dioxide. So that means there's more CO2 going into the ocean, which is still making it acidic. It's not super acidic because of this thing equilibrium, which is also sending CO2 out. But we are still making our oceans acidic.